All right. So now let's ask another question. Now we presumably you know how to get the right answer. I hope. And now we need to understand why. Why do we have orbital hybridization? Now, there's a reason why I asked you to draw. And actually, if you, I'm not sure if you realize it, I didn't ask the orbital hybridization for H2. And the reason I didn't ask is because there is actually no orbital hybridization for H2. Okay, and that's also the reason why for this table, I did not include one electron density. Okay, so let's start off with a few questions. Okay, let's start off with H2. Now we know how to draw this diagram, right? The Lewis dot structure of H2. That's like this. But what is happening here? Let's draw some previous knowledge of earlier course materials. Do we know how to draw the orbital diagram for hydrogen? Well, that's 1s1, right? So you have an up arrow right here. And you look at the Lewis dot structure, there's a line, this covalent bond between the two hydrogen atoms. And that's because they're both sharing the only electron with each other. So therefore they have two electrons, which makes them very stable. Okay, so hydrogen is one of the exceptions. It doesn't need 8, it only needs 2. So what happens is this. When we have a single bond, or we can ask a question. What is a single bond? What is a single bond? Okay, or later on, we actually call this a sigma bond. Okay, what is it? Okay, well, what it really is something like this. We have one hydrogen atom, like this. That's the electron cloud of in the 1s orbital. And then we have another hydrogen. They will come close to each other, and there is a little bit of an overlapping of the s orbitals of these two hydrogen atoms. And this overlapping of s orbitals, it's what we call a single bond or sigma bond. Okay? A single bond or a sigma bond is the overlapping of s orbitals. Okay? All right? So I think that's pretty easy to understand. So if I go back to the orbital diagram right here, so what is really happening is that the other hydrogen atom, and there's an electron from the other hydrogen atom, well, comes into the slot. So they're overlapping, and that's how they built this covalent bond. Okay? So far, so good. Now, that's also the reason why we say there's no orbital hybridization, because it is just the good old, s orbital making this overlapping, and that's okay. And now let's shift gear to methane. And let's just say, what is the orbital diagram for carbon? Is it carbon? It's 1s2, right? And then 2s2, and then 2p2. So, and the Lewis dot structure for methane goes like this. Now, I'm not sure if you are a careful observer. You may go ahead and pause the video right now and see if there's any kind of discrepancy on this diagram and the orbital diagram here, the Lewis dot structure and the orbital diagram. Okay, so the discrepancies are the following. One, based on whatever we just discussed, a sigma bond or a single bond it's an overlapping of s orbitals, right? So if we see the single bonds between carbon and hydrogen, then we probably would assume that there must be some sort of overlapping of s orbitals between C and H, between carbon and hydrogen. But wait, look at the s orbitals, or look at the 2s orbital specifically, because it's in the outermost energy level. It is occupied, it's fully occupied. There's no way to make a bond with the 2s. There's no overlapping. There's no spot to overlap. Then how on earth we have these 4 single carbon-hydrogen bonds? That is so weird. Okay, so no s orbital available from carbon to overlap with hydrogen's s orbital. That's strange. How can we not have available s orbitals and yet making these 4 single bonds? That's weird. Okay. What else is weird? Well, another thing that's weird is that wait, if you look at the orbital diagram, there are only 2 unpaired electrons. So if it's going to make a bond, so only 2 bonds maybe? Only 2 unpaired electrons on carbon. Now, how can it make 4 single bonds? That's weird. That is weird. Okay. And then another thing that's also very weird is that all CH bonds in methane are, well, presumably identical in terms of the energy. Okay. You wouldn't expect that one carbon-hydrogen bond is more challenging to break than the other 3 carbon-hydrogen bonds. But then 2s and 2p, they are slightly different in terms of energy. So how can we explain this discrepancy? Okay. So in order to explain all these phenomena, like how can we have 4 bonds? Well, in order to have 4 bonds, that means you got to have 4 unpaired electrons, right? Wait, hold on. How many electrons are there in the second energy level? 1, 2, 3, 4. That's interesting. And then we say, wait, hold on. How many orbitals are there in the second energy level? 1, 2, 3, 4. So if CH4 is capable of making 4 single bonds, what could likely happen is this. After hybridization, these 4 orbitals, namely 1 2s orbital and 3 2p orbitals, they will hybridize to become 4 of the 2sp3 orbitals. That's how we get the name sp3, is because it's the hybridization product of 1 of the s and 3 of the p's. And then after they merge, and we just go ahead and use Hund's rule to distribute those 4 valence electrons. 1, 2, 3, 4. Sorry for my 3rd electron. Okay, all right. And now every single orbital right here has a little bit of the s characteristic. And to be specific, it's sp3, right? So s is like one of the 4 orbitals. So therefore, we would claim that the sp3 hybridized orbitals would have 25% of s orbital characteristic. And if you are interested in the shape, now s orbital looks like this, p orbital looks like this. Well, what about the sp3 orbitals? It looks like this. Okay, so why? It's more mathematical, and I'm just going to say it's by observation, okay, or by mathematics that we know the shape of the orbitals. So that's how we explain the existence of the 4 single bonds between carbon and hydrogen. That's how we can explain that carbon at the beginning, which has no available s orbital for overlapping, and now it has 4 orbitals with s orbital characteristics. to overlap with the s orbital of the hydrogen atoms. Okay, so that's how we have 4 sigma bonds. All right, now, since we're talking about carbon, let's talk about CO2. And we know the drawing of CO2 is like this, right? So, and we say, oh, what is the orbital hybridization for carbon? In this case, it's sp, not sp3, but just sp. Well, how does it work? Well, this is the original carbon, right? So, after hybridization, it becomes something like this. So this hybridization only involves one of the 2s and one of the 2p orbitals, or one 2s and one of the 2p orbitals. So therefore, just 2 orbitals being hybridized, and the rest are just 2p. And we will distribute the electrons like this. Now, it is very important to understand that these 2 electrons will be responsible for the sigma bond, or the first bond, okay? And let me go ahead and label it. Let me go ahead and label it right here. So consider this as the first bond. That's a sigma bond. And then the so-called double bond, which will be here, they are responsible by the electrons in the 2p orbitals. And we actually have a very special name for this kind of bond. We call them the pi bond. If you go onto the internet, if you Google search pi bond, you actually see a diagram that looks like this. Okay, so it is the overlapping of p orbitals, and that looks like a pi, and that's why we call them pi bonds. So the count of these orbitals here would be 2 sigma and 2 pi. Okay, every single bond, every double bond, it's 1 sigma and 1 pi. Okay, and this is how we see the orbital hybridization, and this is also how we see the formation of these bonds. So it is very important to know orbital hybridization, and in addition to knowing how to tell, it is important to know how to explain it and how we see the sigma and pi bond. Now, there were 2 blanks I didn't answer earlier. What about if you have 5 and 6 electron densities? These are the cases where we exceed octet, okay? And, well, we only have 3 p orbitals, right? So if you use up all the p orbitals, what else do we use? D. And this is the reason why we say who are capable of exceeding octet? Only the elements in the 3rd period and beyond. So in other words, no elements from period 1 or period 2 could exceed octets, but anything from the 3rd period and beyond, for example, phosphorus, sulfur, chlorine, and anything else beyond, they are capable of exceeding octets because they have access to the D sublevel. They can use and hybridize the orbitals from the D sublevel to accommodate more electrons. So that's how we do, how we name the orbital hybridizations by simply counting the number of electron densities. And I hope you understand the explanation and how the orbital hybridization works with the counting of sigma bond, or the formation of sigma bonds and pi bonds. Okay.